A Venn diagram or set diagram is a diagram that shows all possible logical relations between a finite collection of sets. Venn diagrams were conceived around 1880 by John Venn. They are used to teach elementary set theory, as well as illustrate simple set relationships in probability, logic, statistics, linguistics and computer science. Example. This example involves two sets, A and B, represented here as colored circles. The orange circle, set A, represents all living creatures that are two-legged. The blue circle, set B, represents the living creatures that can fly. Each separate type of creature can be imagined as a point somewhere in the diagram. Living creatures that both can fly and have two legs are for example, parrots are then in both sets, so they correspond to points in the area where the blue and orange circles overlap. That area contains all such and only such living creatures. Humans and penguins are bipedal, and so are then in the orange circle, but since they cannot fly they appear in the left part of the orange circle, where it does not overlap with the blue circle. Mosquitoes have 6 legs, and fly, so the point for mosquitoes is in the part of the blue circle that does not overlap with the orange one. Creatures that are not two-legged and cannot fly would all be represented by points outside both circles. The combined area of sets A and B is called the union of A and B, denoted by A or B. The union in this case contains all living creatures that are either two-legged or that can fly. The area in both A and B, where the two sets overlap, is called the intersection of A and B, denoted by AA copyright B. For example, the intersection of the two sets is not empty, because there are points that represent creatures that are in both the orange and blue circles. History. Venn diagrams were introduced in 1880 by John Venn in a paper entitled On the Diagrammatic and Mechanical Representation of Propositions and Reasonings in the Philosophical Magazine and Journal of Science, about the different ways to represent propositions by diagrams. The use of these types of diagrams in formal logic, according to Ruski and M. Weston, is not an easy history to trace, but it is certain that the diagrams that are popularly associated with Venn, in fact, originated much earlier. They are rightly associated with Venn, however, because he comprehensively surveyed and formalized their usage, and was the first to generalize them. Venn himself did not use the term Venn diagram, and referred to his invention as Eulerian circles. For example, in the opening sentence of his 1880 article Venn writes, "Schemes of diagrammatic representation have been so familiarly introduced into logical treatises during the last century or so, that many readers, even those who have made no professional study of logic, may be supposed to be acquainted with the general nature and object of such devices. Of these schemes one only, viz. that commonly called Eulerian circles, has met with any general acceptance." The first to use the term Venn diagram was Clarence Irving Lewis in 1918, in his book A Survey of Symbolic Logic. Venn diagrams are very similar to Euler diagrams, which were invented by Leonhard Euler in the 18th century. Emma E. Barron has noted that Leibniz in the 17th century produced similar diagrams before Euler, but much of it was unpublished. She also observes even earlier Euler-like diagrams by Ramon Lull in the 13th century. In the 20th century, Venn diagrams were further developed. D. W. Henderson showed in 1963 that the existence of an n-Venn diagram with n-fold rotational symmetry implied that n was a prime number. He also showed that such symmetric Venn diagrams exist when n is 5 or 7. In 2002 Peter Hamburger found symmetric Venn diagrams for n equals 11, and in 2003, Griggs, Killian, and Savage showed that symmetric Venn diagrams exist for all other primes. Thus rotationally symmetric Venn diagrams exist if and only if n is a prime number. Venn diagrams and Euler diagrams were incorporated as part of instruction in set theory as part of the new math movement in the 1960s. Since then, they have also been adopted by other curriculum fields such as reading. Overview. A Venn diagram is constructed with a collection of simple closed curves drawn in a plane. According to Lewis, the principle of these diagrams is that classes, or sets, be represented by regions in such relation to one another that all the possible logical relations of these classes can be indicated in the same diagram. That is, the diagram initially leaves room for any possible relation of the classes, and the actual or given relation can then be specified by indicating that some particular region is null or is not null. Venn diagrams normally comprise overlapping circles. The interior of the circle symbolically represents the elements of the set, while the exterior represents elements that are not members of the set. For instance, in a two-set Venn diagram, one circle may represent the group of all wooden objects, while another circle may represent the set of all tables. The overlapping area or intersection would then represent the set of all wooden tables. Shapes other than circles can be employed as shown below by Venn's own higher set diagrams. Venn diagrams do not generally contain information on the relative or absolute sizes of sets. That is, they are schematic diagrams. Venn diagrams are similar to Euler diagrams. However, a Venn diagram for n-component sets must contain all 2n hypothetically possible zones that correspond to some combination of inclusion or exclusion in each of the component sets. Euler diagrams contain only the actually possible zones in a given context. In Venn diagrams, a shaded zone may represent an empty zone, whereas in an Euler diagram the corresponding zone is missing from the diagram. For example, if one set represents dairy products and another cheeses, the Venn diagram contains a zone for cheeses that are not dairy products. Assuming that in the context cheese means some type of dairy product, the Euler diagram has the cheese zone entirely contained within the dairy product zone. There is no zone for non-dairy cheese. This means that as the number of contours increases, Euler diagrams are typically less visually complex than the equivalent Venn diagram, particularly if the number of non-empty intersections is small. Extensions to higher numbers of sets, Venn diagrams typically represent 2 or 3 sets, but there are forms that allow for higher numbers. Shown below, 4 intersecting spheres form the highest order Venn diagram that has the symmetry of a simplex and can be visually represented. The 16 intersections correspond to the vertices of a tesseract. For higher numbers of sets, some loss of symmetry in the diagrams is unavoidable. Venn was keen to find symmetrical figures, elegant in themselves, that represented higher numbers of sets, and he devised a 4-set diagram using ellipses. He also gave a construction for Venn diagrams for any number of sets, where each successive curve that delimits a set interleaves with previous curves, starting with the 3-circle diagram. Edwards Venn diagrams. A.W.F. Edwards constructed a series of Venn diagrams for higher numbers of sets by segmenting the surface of a sphere. For example, 3 sets can be easily represented by taking 3 hemispheres of the sphere at right angles. A 4th set can be added to the representation by taking a curve similar to the seam on a tennis ball, which winds up and down around the equator, and so on. The resulting sets can then be projected back to a plane to give cogwheel diagrams with increasing numbers of teeth, as shown on the right. These diagrams were devised while designing a stained glass window in memory of Venn. Other diagrams, Edwards Venn diagrams, are topologically equivalent to diagrams devised by Branco Gra 1/4 NBAUM, which were based around intersecting polygons with increasing numbers of sides. They are also 2-dimensional representations of hypercubes. Henry John Stephen Smith devised similar n-set diagrams using sine curves with the series of equations. Charles Lutwidge Dodgson devised a 5-set diagram. Related concepts. Venn diagrams correspond to truth tables for the propositions, etc., in the sense that each region of Venn diagram corresponds to one row of the truth table. Another way of representing sets is with the diagrams. See also, logical connectives, notes. References. Further reading, Generalized Venn Diagrams 1987 by E. S. Mahmudian, with M. Rize and F. Botten. A Survey of Venn Diagrams by F. Ruski and M. Weston, is an extensive site with much recent research and many beautiful figures. Stewart, Ian. Ch4 Cogwheels of the Mind. Another fine math you've got me into. Dover Publications PPA 51 €64. ISBN A0-486-43181-9. Edwards, A.W.F. Cogwheels of the Mind, The Story of Venn Diagrams. JHU Press. ISBN A978-0-8018-7434-5. Venn, John. On the Diagrammatic and Mechanical Representation of Propositions and Reasonings. Dublin Philosophical Magazine and Journal of Science 9, 1 Euro 18 doi, 10.1080/14786448008626877. Ruski, Calais. Ruski, Frank. A New Rosie the First Simple Symmetric 11 Venn Diagram 1207. PA 6452. AR Ziv, 1207.6452. Bibcode, 2012 AR Ziv 1207.6452. MAR, external links, Haswinkel, Michiel, ed., Venn Diagram, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Weierstein, Eric W., Venn Diagram, MathWorld. Free software for generating Venn and Euler diagrams using circles. Lewis Carroll's Logic Gamer Venn vs Euler at Cut the Knot, a survey of Venn diagrams, area proportional three-way Venn diagram applet, generating Venn diagrams to explore Google suggest results, 7 sets interactive Venn diagram displaying color combinations, 6 sets Venn diagrams made from triangles, postscript for 9 set Venn and more, VBVNN a visual basic program for calculating and graphing quantitative two-circle Venn diagrams.